Good morning, dear all, and let's start our today lecture. And the main object of first part of our lecture is hyperbola. I recall the basic definition which was done in the previous lecture, and we consider some basic properties of the hyperbola. I recall that the definition of the hyperbola is the same as the definition of the ellipse, and hyperbola is uniquely defined by some fixed point f and straight line L. More precisely, given a fixed point f and a fixed straight line L, we have some point and the straight some point. I'm sorry, the fixed point f and the straight line L. Good morning. Hyperbola is the locus of a point P which moves so that the ratio distances from P to F and P to R from P to L is a constant which greater or equal which greater than 1, and let's consider the some perpendicular which pass through P perpendicular to L, and let the point R be the point of intersection or the base of this perpendicular. And in our picture, the ratio of distance P from P to F and P to R is constant. P is moving point. And let's consider some straight line which pass through F and perpendicular to L, and let K be the point of intersection, this perpendicular and our straight line L. And let's consider the point A which lies on this perpendicular such that the ratio of distance AF to AK is also E. This point other belongs to our locus, belongs to the future conic section which we call the hyperbola. Our aim to define the new conic section hyperbola as a geometrical locus which point of this geometrical locus are satisfy some equation, and our aim to deduce the equation from this geometrical definition. And let's start. First of all, let's observe some basic relation between main geometrical object in our case. Let's consider the other point A prime, which lies on the perpendicular which pass through point A perpendicular to a straight line. This point which satisfy the same relation A prime F, A prime K is also equal E. This two symmetric point. Oh, I'm sorry, this two symmetric point. And let's O be the middle of segment A prime. O be the middle of A prime A. And first of all, we shall compare, we are going to compare the distance, three distances OK, OA, and OF. First of all, let's compare. Excuse me. Let's compare three distances. This one, and this one. And this relation we can use to deduce the equation of our curve hyperbola. And we'll see that this relation will be the same as the relations in the case of ellipse. And our reasoning will be the same. First of all, easier to see that we have also the same point K, which will be symmetric point K onto our fixed point O, or the middle of the segment A prime. So we have O A prime is equal, the distance O A prime is equal OA. And first of all, let's consider two expressions. First of all, A prime F minus AF. A prime F easy to see that this relation is exactly equal the distance between A prime A. Excuse me, and we can suggest that the distance A prime A is equal to A, to little a. So that OA, the distance OA and distance between OA prime are equal and equal A. We introduce this first parameter which define our section line, our conic section hyperbola. And easy to see that this difference exactly equal to A, to small a. Easy to see from this relation follows that the length of the segment AF is equal the product E and AK. Easy to see that we have two consequences. AF is equal E AK and A prime F is equal A prime K. The product E and A prime K. And we obtain that this difference is equal product E, and on difference A prime K and AK. A prime K minus AK. If we consider the same point K prime, which symmetric K onto A, easy to see that distance A prime K minus AK is equal difference A prime K minus A prime K prime, and exactly equal distance between K prime K. This one minus this one. This one is equal this one. And this one minus this one is equal this one minus this one. And this difference exactly equal the distances between points K prime and K. Do you understand this reasoning? And A prime K minus AK is equal A prime K prime and equal K prime K, and this distance, this distance A O prime K. And we obtain the first relation. O K prime is equal the ratio A and E. From this relation, it follows that 2A is equal A the product A and twice OK, and we obtain that A is equal product E and OK, and we obtain the first relation. To obtain the relation between OF and OA, we consider the sum, the sum A prime F and AF. A prime f plus a f. Easy to see. A prime f, a prime f plus af is equal let's consider the other point to f prime, which also symmetric point f onto the point O. And easy to see the sum a prime f, a prime f plus af is equal f prime a prime plus a prime a. Easy to see, the sum is equal a prime f plus a prime f prime, and is equal to OF. And from this relation, easy to see that a prime f is equal E, the product E and a prime k. And this one, a prime f, is equal E, the product E and a prime k. And this one, AF, is equal E distance AK. As was mentioned above, the sum of distances A prime K and KA is exactly equal distance between point A prime A. This distance. And we obtain the following sum A prime K plus AK, and is equal E A prime A, and is equal E to A. And compare this expression and this, we obtain that twice OF is equal twice EA. And we obtain the second basic relation, OF is equal product EA. We obtain the following basic relation. First of them, OK is equal the ratio AE, and OF is equal product EA. We obtain the same relation as the case of the ellipse. It's absolutely same. But in the case of the hyperbola, the parameter E is greater than 1. In the case of the ellipse, this parameter less than 1. Only this difference between two cases. And now let's try to obtain the equation which define our geometrical locus. And as above, in the case of ellipse, let's consider the coordinate system which has O as origin and axis OX will be coincide with our perpendicular, which pass from F perpendicular to L, OX, and other axis, OY, is parallel to our straight line A. And let we also have the straight line L prime, which symmetric straight line L onto origin O. And let's consider our moving point P, and we will suggest that P has coordinates x and y, and we will use the definition of ellipse. Definition. The definition is the following: the distance P, the ratio PF to the ratio PF to PR is equal epsilon, is equal E, our definition. Let's calculate the distance PF and PR and compare each expression for these distances. And using this relation, we obtain the definition our locus as a set of points which satisfies this equation. First expression for PF. We have that the coordinates of the point P is equal xy, and coordinate of the point F is equal E, the product E and A, and the second coordinate y is equal 0, and we have this coordinate. We want to consider this distance. We can use the Pythagorean Theorem, and this distance is equal sum of squares, differences between corresponding coordinate of point P and point F. The difference between coordinate x is equal E A minus x model of this difference, and this difference between second coordinates is equal y, and we obtain that distance is equal root square from EA minus x square plus y square, and this difference, and this distance. This one, PR, is exactly equal difference between point A and point K. I'm sorry, between straight line K and point X. PR is equal the coordinate of point K is equal the ratio AE. Okay, is equal AE. And this coordinate of point R is also equal AE. And this distance PR, which is equal X minus the ratio AE. And we can use this definition. PF is equal E times PR. And from this equality, we obtain that product E PR is equal E X minus A. And using this expression, we obtain that the PF square is equal the product E PR square. And we obtain EA minus X square plus Y square is equal square of this expression, X minus A square. And we obtain this relation. Let's simplify this expression, and after the simplification, we obtain the equation, the defining equation of hyperbola. And we can we will compare left hand and right hand of this equality. After the evident simplification, we obtain E square A square minus twice EA X plus X square plus Y square is equal E square X square minus twice EA X plus A square. We will subtract this expression, and I call that E greater than 1. And we can rewrite this expression in the following form. This one and this one. We obtain E square minus 1 X square minus Y square. This one and this one we can simplify, and using distributivity law we obtain E square minus 1 A square. And we can divide on this expression left side, and we obtain the ratio x square a square minus y square e square minus 1 is equal 1. Let's introduce the new parameter. Oh, I'm sorry, the product e square minus 1 and a square. And let's denote by b square this expression, e square minus 1 a square, and we obtain final expression as the same form as the defining equation for the ellipse, but in the ellipse we have the sign plus, and in the case of hyperbola we have sign minus. Only this difference. The form is the same. And in our case, we also this expression e square a square is exactly the distance between O and F. And let's consider this distance by c, by small c. And we obtain this expression b square is equal c square minus a square, or c square is equal a square plus b square. In the case of ellipse, in this case we have also sign minus. In the case of hyperbola, plus. How we can try to draw the hyperbola on our picture. The moving point P move such that this ratio is constant. In this point, the ratio between P coincides with K, and the distance between K and O is minimal. And we have exactly such curve. Each curve is symmetric onto point O, and we have two branches of our curve, this right branch and the left branch. We change A prime, yes. We have the symmetric other straight line A prime, and we have other branch of the hyperbola. This equation is symmetric onto x and OY, and we can see that our curve is symmetric. I'm sorry, maybe a mistake. Sorry, mistake. Excuse me. Okay, OA, this one A. Symmetric A is directrix, and this A. This distance A, this distance the ratio AE, and this distance the ratio AE. This distance A, and here, and we have also the other point B and B prime, and we have basic rectangle. Basic rectangle. This side of the rectangle is equal to A, and this side to B, twice B. And in the case of hyperbola, we have also the same base rectangle of our curve. This rectangle has the two sides. One of the side is equal to A and other to B. And we'll use this rectangle to define two other straight line, which we will call asymptotes. What does mean the term asymptote? The asymptote is such straight line. We have arbitrary curve in the plane. The asymptote are this such straight line such that the distance between this straight line and point which moves on our curve, when this point moving goes to infinity, this distance goes to 0. And we prove that in the case of hyperbola, two straight lines which defined by equation y is equal plus minus the ratio b a x, and these two curves is asymptotes in and satisfy this definition. But first of all, we prove the theorem which gives the other definition of our pure hyperbola. We introduce the point f prime, which is symmetric point f onto origin of our coordinate system. And the main result is the definition of hyperbola in terms of distances between arbitrary point of curve from f and f prime. The main theorem asserts that the difference distances between p f prime and p f is a constant, and is equal to IC, the main result. And let's prove this theorem. theorem. The difference distances this point f and f prime as in the case of ellipse we will call foci and 2 point, and the theorem asserts that the differences of the distances from the foci f and f prime to any point of hyperbola is a constant and equal namely the sum, the difference p f prime minus p f is equal to a. We have the point P which has a coordinate x, y. We have f and one focus f and other focus f prime, and we have two distances f f prime f prime p is distance to point P, and the distance P prime Q this ratio is equal epsilon and the distance PF and I'm sorry FA I try to draw better. F prime F, A, to straight line L and L prime, this distance and this distance. And you consider 2 point Q prime and Q. Q prime and Q. And let xy and will be coordinates of the point P. And let's calculate these distances. F prime P is equal P PQ prime, the distance between P and directrix, the symmetric directrix. PQ prime and PF is equal and let's Q be the point which is the base of perpendicular to point which through point P perpendicular to straight line A. The point Q, the point of intersection of this perpendicular and straight line A, and PF is equal E PQ. This distance PQ is equal E. P has coordinate x minus this distance, the ratio this distance the ratio AE, and we have this ratio EX plus this expression is equal product E and distance PQ prime. PQ prime is equal x plus this distance. This distance is equal the ratio AE. And the same way we obtain that product E PQ is equal E x minus the ratio AE. And we obtain that this difference F prime P minus PF is equal this difference E x plus AE minus E x minus AE, and we obtain this product A plus A plus AX minus AX. We can subtract, and A plus A is equal to A. And we obtain the assertion of this theorem. And the main observation is that the distance PQ prime is equal the sum x and this sum, which equal the ratio AE. Maybe an equation. Do you understand? What? Explain. Yes. Okay. Maybe I draw the better this picture. The main tools of our proof, these two equality, and I repeat my reasoning. We have the point F, point A, and point K. I repeat the notation in the previous picture, and we have K, and we have also point O and point K prime is symmetric K, A prime is symmetric A, and F prime is other focus which symmetric F. And I can restore the base rectangle, and I have the arbitrary point which has a coordinate xy. The coordinate x, this coordinate, and I have also point K is point of intersection the directrix with axis OX, and K prime is also point intersection of directrix. It's the symmetric point. And we have two distance, PF and PF prime. And I'm going to consider the difference, this distance and this distance. I have two basic relation which define hyperbola. This distance is equal the distance from this point to directrix multiply on epsilon or on E. This is definition of hyperbola. And let Q will be the base of perpendicular which pass through P perpendicular to straight line A to directrix. And symmetric, and we have also symmetric point Q prime, which lies on symmetric directrix L prime. And we have also the distance between P Q prime and distance between F prime P. And the ratio of this distance to this distance is the same, constant, and is equal E, the other relation. We have two relations, this one and this one. And our aim to consider the difference between this one and this one. And let's calculate the distance Q prime, this distance, and this distance, PQ. This distance, easy to see, equals this one. P has coordinate x, and this coordinate is this, in this. The point K has coordinate the ratio AE, and this difference is equal x minus ratio AE. This one. This one. This one. X, this, OX, and plus this one. But K prime has coordinate minus the ratio AE 0. And this difference is the sum. This one, which equal x, and this distance, which equal the ratio AE. And in this case, we have sign plus, x plus the ratio AE. And we subtract from this expression this one, because this expression is equal f prime p, and this expression is equal pf. And we have the difference between these two expressions. And I subtract from this expression. And if I multiply E on this expression, I obtain EX plus A. And in this case, multiply E on X, and I have EX, and minus A. And after subtraction, I obtain subtract EX and minus EX, yield one another, and I obtain A plus A, and is equal to A. And our theorem, and this relation is exactly assertion of our theorem. And I obtain the other equivalent definition of the hyperbola. Hyperbola is the locus of the moving point P such that the difference between this point and the two fixed points f and f prime is constant and is equal twice A as a definition. Maybe any question? Do you understand this simple assertion? Okay, let's continue. And the last expression will be a description of the asymptotes. I am going to prove that the curve which defined by this formula, y is equal plus minus the ratio BAX, these two curves are asymptotes. We have, I restore the previous picture. We have f and f prime foci, A prime, B prime, and we have the base rectangle, and we have a straight line. This straight line y is equal. There should be ax, and this straight line minus. There should be a times x. And we have L and A prime our directrices. And the first branch of hyperbola has the following and we have 2 points P, the point which moving on our hyperbola, and the point P prime, which has the same coordinate as the P, but moving on the our asymptote, which has coordinate y is equal, there should be a times x. And our claim to calculate the difference between to calculate the distance between 2 points. These 2 points have the same coordinate x, and the difference is exactly equal the difference between coordinate y. These 2 points. And let's calculate this difference. P has coordinate h. We have the following expression for hyperbola x square. There is x square a square minus y square b square is equal 1. And in this case, we can express y in terms of x. We obtain the ratio y square b square is equal x, the ratio x square a square minus 1, and y square is equal b square a square x square minus a square and we obtain y is equal, there should be a x square minus a square minus a square. The second coordinate is equal b a x square minus a square. And P prime has coordinate h. Oh, I'm sorry. H. I change x on h. The coordinate of the first coordinate. And in this case, we have coordinate h, b, a, h. And the distance between these 2 points is equal difference between second coordinates. namely,
sorry.
yes?
Shouldn't it be b squared, y squared is equal to b2 over a2 times x2 minus b2, not a2. Down. Yes.
Yes. Maybe repeat our calculation. Yes. Maybe x square minus a square. I rewrite this expression is in this form after multiply left and right side b square and apply root square operation. This one and this one, and I consider only sign plus in this case. The other cases we can consider analogously the same way. Do you understand this, right? Right formula? Yes. Okay, and in this case we consider the distance p prime. This distance p prime is equal difference between the values of coordinate y for this point and this point. Because if we have the same one of the coordinates, the distance is equal exactly difference between other coordinates. Using this fact, it follows from Pythagorean Theorem. And in this case, we obtain this difference BAH minus BA root square H square minus A square. And this difference, easy to see that this difference is equal. This we have difference between two expressions, and we can use the formula u minus vu plus v is equal the difference square u and v, and multiply this difference on the same sum and divide it on the same expression. And denominator is equal b the ratio b square a square h square minus the square of this expression b square a square h square plus b square subtract a square and a square. And we obtain the following expression: b the ratio b square and ba h plus h square minus a square. We substitute b and a, and we obtain the final formula AB, the ratio AB, H plus H square minus A square. And this expression goes to 0 when H goes to infinity. Easy to see. H goes to infinity, and this expression in denominator goes to infinity, but nominator is constant, and the ratio goes to 0. And we obtain that this straight line is actually asymptotes. Any question, maybe? Okay. And let's pass to the part 2 of our lecture. Part 2. In the part 2, we consider the general equation of the conic general equation. We shall consider the most general equation in the form of polynomial of degree 2, and we shall call the geometrical locus of the point which satisfies this equation the curve of second order. And our claim to prove that any curve of second order is a curve which is the same as the one of the conic section. But exactly, we have other so-called exceptional cases. For example, x squared is equal 1 is not, this equation is not defined the conic section. In our case, x is equal plus minus 1, and we have two parallel straight lines. And we have also other euclidean cases, and we formulate the exact theorem which describe only any cases for geometrical locus or for the equation which is a polynomial of degree 2. But in the situation of general position, we obtain conic section. And we have this general equation. Arbitrary second degree equation. Our aim to describe the geometrical locus of the point which satisfies this second degree equation. First of all, consider the partial case when the coefficient b is equal 0, namely ax squared plus cy squared plus 2 dx plus 2 ey plus f is equal 0. I recall, if we have, for example, equation of the ellipse x squared, the ratio x squared a squared plus y squared b squared is equal 0. and we moved the origin of the coordinate system, we obtain the equation in the following form. And if x0, y0 is the origin of a new coordinate system, in this new coordinate system we obtain the canonical equation of ellipse. This same way we can shift the hyperbola and consider the equation of hyperbola in the shifted coordinate system. And in this shifted coordinate system, the equation of hyperbola has the following form. And x0, y0 is the coordinate of the center of hyperbola or ellipse. The same way, we obtain the equation of the parabola. The canonical equation is equal y squared is equal to px, and shifted equation has the following form. And our claim to prove that the equation in this form can be reduced to one of this form. More generally, in this case, we obtain some values. In this case, maybe plus, minus 1 or 0. And in this case of plus, we obtain ellipse. In the case of the 0, we obtain only 1 point. And in the case minus 1, we obtain so-called imagine ellipse. And we have also the same case for other cases. More precisely, we can let's suggest that a square plus b square is not 0. And more precisely, a is not 0 and b is not 0. Case 1, 1. In this case, we can rewrite this equation in the same way. X squared plus the ratio 2d divided ax plus c y squared plus f is equal 0. We can rewrite this expression as a square of the difference, namely x plus the ratio dA square minus d square a square. This expression I can rewrite in this following form. And this expression, the same way, I can rewrite in the following form: plus c y plus the ratio EC square minus the ratio E square C square, and plus F is equal 0. After then we obtain the following expression. We obtain the following expression. X plus the ratio dA square plus C the ratio y plus the ratio EC square minus the ratio D square A minus E square C plus F. Just 1 or maybe 2 minutes and I finished. Yes, we can denote by x0 minus dA. Yes, thank you. And y0 we can denote by minus EC, and this expression we denote by minus G, and we obtain the following expression: x minus x0a plus c y minus y0 is equal to G, and finally we obtain the following expression. The first case, we suggest that G is not equal to 0. If G is equal to 0, we obtain that this equation defines only one point, x0, y0. If G is not equal to 0, we suggest that A is not 0, is not equal to 0, and C is not equal to 0. And in this case, we obtain two cases. First, if this sign of this expression is the same. If the sign is positive, we obtain ellipse. If the sign is negative, we obtain imaginary ellipse. It's empty set. But in complex plane, we obtain some complex curve. If the sign of this expression is different, we obtain, in this case, hyperbola. Right hand is not equal to 0. And the last case, when one of this parameter or C is equal to 0. In this case, we obtain parabola. And all these cases we consider on next our seminar. And last remark. The general case can be reduced this case, and we consider how to reduce this case to this, how to kill the parameter B. The parameter B can be killed by using rotation of coordinate system. And we consider on the next lecture how rotate the coordinate system to kill this parameter b. And we reduce general case to this partial case. Thank you for attention. Maybe a question? Any question? Thank you for your attention, and let's finish our lecture.